For a circle of radius r, a central angle theta in radians intercepts an arc of length s given by s equals r theta. S is the arc length of the outer part of your sector. R is the radius of the circle, and theta is the central angle in radians. Consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time, t, then the linear speed v of the particle is s over t. So the linear velocity of a particle out here on the arc is the distance traveled divided by the time traveled. Velocity is distance over speed. Excuse me, distance over time. Distance over time. If theta is the angle in radians corresponding to the arc length s, then the angular speed omega, it just looks like a smooth W, but that's the Greek letter omega, of the particle is the amount of angle swept in a given amount of time. So linear velocity is the arc length traveled over a set amount of time. Omega is the amount of angle swept over a certain amount of time. Now, linear speed measures how fast the particle moves, and the angular speed measures how fast the angle changes. Well, since arc length is radius times theta, if you divide both sides by t, s divided by t is linear velocity. R times theta divided by t, well, that's r times omega. Omega was theta divided by t. So there's a nice relationship. If you know the angular velocity and the radius of your circle, then you can calculate the linear velocity of the particle out on the edge. Also recall that for a circle of radius r, the area of a sector of the circle with central angle theta in radians is A equals 1/2 times r squared times theta. And we calculated some area formulas, or some areas on the previous videos using this formula. The key is for any of these, make sure theta is in radians and not degrees. A car's rear windshield wiper rotates at 120 degrees. The total length of the wiper mechanism is 21 inches. The length of the wiper blade is 15 inches, so that leaves a difference of 6 inches. Find the area wiped by the wiper blade. Okay, so the strategy is this part will be wiped by the blade, so I want to find the area of the entire sector and then remove the area of that unwiped sector. So 1/2 times 21 squared, 120 degrees is equivalent to 2 pi over 3 radians. And so that's, in the green box, that's the area of the entire sector. Minus this empty space that doesn't get wiped, that's 1/2 times 6 squared times 2 pi over 3. All of it minus the little bit that doesn't get wiped gives you the area of the wiped section. The wiper takes 1 second to rotate and return to its starting position. Find the angular speed in radians per second of the tip of the wiper blade. So the blade goes down and back 120 degrees down, 120 degrees back. So that's a total of 240 degrees in 1 second. Now with omega, we've got to convert 240 degrees to radians. 240 over 180 reduces to 4/3. So 240 degrees is equivalent to 4 pi over 3. Now, because the blade makes its trip in 1 second, dividing by 1 is going to let it stay at 4 pi over 3 radians per second. 4 pi divided by 3 is approximately 4.19 radians per second. Does the entire wiper blade move at the same angular speed? Each point on the blade goes through the same angle in that 1 second, 120 degrees each way. So any point anywhere on the blade is going to move at 4 pi over 3 radians per second. So the answer to the question is yes, each point on the blade moves through the same angle. Find the linear speed in inches per second of the tip of the wiper blade. Round your answer to 1 decimal place. Okay, so remember the mechanism is 21 inches long total. We want to know how fast a place on the tip of the blade is moving when it swipes. Recall that linear velocity is equal to radius times angular velocity. Well, on the previous slide, we found the angular velocity to be 4.19 radians per second. The radius is 21 inches, so 21 times our angular velocity is approximately 88 inches per second. So that tip of the blade is hauling 88 inches in 1 second. Does the entire wiper blade move at the same linear speed? Well, since V is directly dependent upon radius, they don't. Even though you're moving the same amount of angle, the distance traveled gets longer than you do, like say in the middle of the blade, there's not as much distance traveled in the same amount of time. So the answer to this one is no, the base of the blade moves slower than the tip of the blade. And since linear velocity is distance traveled over time, the longer that arc is, the faster that object is traveling. A carousel with a 40-foot diameter makes 5 revolutions per minute. Find the angular speed of the carousel in radians per minute. Round your answer to 2 decimal places. 5 revolutions. Remember, a revolution is 360 degrees, which is also 2 pi radians. 5 revolutions per minute converted to radians per minute. We're going to say that 1 revolution is equal to 2 pi radians. So that gives us 10 pi radians per minute, which is approximately 31.42 radians per minute. The carousel has a diameter of 40 feet, so that means the radius is half of that. 20 feet is the radius. Find the linear speed in feet per minute of the platform rim of the carousel. Round your answer to 2 decimal places. Okay, so linear speed is radius times angular velocity. The radius of the Ferris wheel or carousel, I think it's carousel in this problem, is 20 feet. Our angular velocity, or the rotational speed, is 31.42 radians per minute. I put this note here, rad has to be here because your angle, if it's angular velocity or omega, it needs to be radians per unit of time. We're asked to find the linear speed in feet per minute, so the radius is in feet. The time component of our angular velocity is minutes, so that's going to work well. 20 times 31.42, that's 628.32 feet per minute. A satellite in circular orbit 1,100 kilometers above Earth makes 1 complete revolution every 140 minutes. Assuming that Earth is a sphere of radius 6,400 kilometers, however you want to pronounce it, what is the linear speed in kilometers per minute of the satellite? Round your answer to 1 decimal place. Okay, so we have 6,400 kilometers to just get to the edge of Earth atmosphere, another 1,100 kilometers to get to the satellite. So our total radius is 7,500 kilometers. The satellite is orbiting 1 revolution in 140 minutes. One revolution is 2 pi radians in a 140-minute time span. I didn't worry about reducing this because we want to know the radius times the angular speed, 7,500 kilometers from the center of the Earth to the satellite. The rotational speed is 2 pi radians in 140 minutes. That's one revolution in 140 minutes. 7,500 times 2 times pi divided by 140. Radians is there. It just tells us that our angle is in the right format. Instead of degrees, it's in radians, and that's what we need. Multiply, divide by 140, we get 336.6 kilometers per minute. Distance per time, and that's what velocity is. The diameter of the drum on an electric hoist is 8 inches. Find the number of degrees through which the drum must rotate to lift a beam 2.5 feet. Now, the drum is given in inches, but the total distance here is in feet. 2.5 feet is the same as 30 inches. Because 1 foot is equal to 12 inches, I can cancel the feet when I set up this conversion. 2.5 feet times 12 inches per foot gives us 30 inches. Now this drum, when it rotates once, because it has a diameter of 8 inches, it has a radius of 4. When this drum makes one full rotation, it lifts 25.13 inches in that rotation. Now, how is that? 2 pi times r, 2 pi times 4, that's the radius, is 8 pi. 8 times pi is approximately 25.13 inches in one rotation. So how many rotations will it take to lift the beam 30 inches? That's the total amount we need to lift it. 25.13 inches per rotation of the drum is going to be equivalent to 30 inches in how many rotations? Well, if we cross multiply, 25.13 times x is equal to 1 times 30. Divide both sides by 25.13. 30 divided by 25.13 tells us that it's a little more than one rotation, 1.19 rotations to be very close. In degrees, a rotation is 360 degrees, so you can cancel those rotations. 1.19 times 360 tells us that the drum would have to rotate 430 degrees in order to lift that beam 30 inches. I hope this video has helped. Please reach out with any questions that you have in class, email, or phone, and I'll do my best to help you out.